What's up, scholars? We're going to talk about arithmetic with radical expressions. Radical. I'm going to say that every time I say the word radical. So radical. All right. We have this beautiful property of radical sums and differences that says if I have some number times, let's say, a root of something plus or minus another number that has the exact same index and the exact same base, then I can just add or subtract those numbers together. As long as the index and the base are the same numbers. Index and base must be equal. So as long as, if they're like, they could both be square roots of the same number, you can add or subtract the number in front of them. It's like this is a variable. This whole, the xth root of n, it's like it's a variable. So if I had, in variable terms, 3x plus 2x, you would say that's 5x. So similarly, we've got something times the xth root of n. Like that's treating that like a variable. Treating that like a variable. We add those numbers in front. So let's look at some examples. Simplify each expression. My computer got for a second. Hold on. Don't know what's happening. It's all very weird. Ghosts. Ghosts is what it is. Ghosts. Cool. It's all fine. It's all fine. It's all fine. Sorry. Simplified expression. The square root of 5xy plus 8 square roots of 5xy. Well, they're both square roots, and they have the same base. They say both got 5xy, so we're good. We can add them up. What number is sneakily in front of this square root of 5xy? It's a 1. There's a 1 there, so this is really 9 square root of 5xy. Cool. B, 6x squared times the square root of 7 plus 4x squared times the square root of 5. Hold on. Those bases are not the same. We can't add those. Can't simplify. Bases aren't equal. They had to be equal. Can't do it, man. That's it. Well, let's try C. 12 times the cube root of 7xy minus 8 times the fifth root of 7xy. We can't simplify that one either, because the indexes aren't the same. Indexes aren't equal. Boring. I don't like when we can't simplify. It's much better when we can. Maybe D will be better. How about 3x times the square root of xy minus 4x times the square root of xy? Oh, great. They're both square roots, and they both have the same base, xy. So we can do the simplification. 3x minus 4x. That's negative 1x, or just negative x square root of xy. Great. Okay. Let's see if we can pump up the jam a little bit. Pump it up. Can we simplify the square root of 12 plus the square root of 75 minus the square root of 3? None of those have the same base. I wonder if I can make them have the same base. Let's do a little factor tree. Let's see what happens here. Square root of 12. Break that down into 4 and 3. Break that 4 into 2 and 2 with the square root. So I need groups of 2. So that's actually 2 square root of 3. Oh, let's see what's happening here. 75 could be 25 and 3, could be 5 and 5, groups of 2. So that's really 5 square roots of 3 minus the square root of 3. Now they all have the same index, 2, and the same base, 3. We can simplify. 2 square root of 3 plus 5 square root of 3 is 7 square root of 3 minus 1 square root of 3 is 6 square root of 3. That was pretty. That I enjoyed immensely. Let's do some more stuff with it, shall we? We shall. Ba-da-da-ba-ba. We added and subtracted. Now we're going to talk about multiplying. We only get to multiply radicals if they have the same index. So the square root of 8a times the square root of 5a, can we even do the thing? Yeah, their index is both 2. So it's like they all went under one house. 8a times 5a cubed. Yep, they all go under one roof. Happy as clams. Let's multiply the things together, go together. 8 and 5 is 40, and a cubed is a to the 4th. Oh yes, so nice. But wait, there's more. Now we can simplify. We can break down 40 into 4 and 10, and 4 into 2 and 2, and 10 into 2 and 5. So it's a square root. Our index is 2, so we're looking for groups of 2. We got 2s and groups of 2. So that 2 is going to be on the outside. And this 2 and 5 will stay on the inside. This a to the 4th is a times a times a times a. Groups of 2 here, groups of 2 here. So we'll have 2a times a on the outside, or a squared, times the square root of 2 times 5, which is 10. There we go. That looks nice. That looks real nice. You know, it looks so nice, I think we should just do it again. The 4th root of 3x times the 4th root of 27x to the 5th. Can we even multiply them at all? Well, yes, they have the same index. Index of 4. So this becomes the 4th root of 3x times 27x to the 5th, which becomes the 4th root of 3 times 27 is 81. X times x to the 5th is, of course, x to the 6th. Alright, well, shall we break it down then? I think so. 81 is 9 and 9, is 3 and 3, and 3 and 3, and 6 x's together. But how many need to go in a group? Well, our index is 4. So we're looking for groups of 4, which we got in the 3s, baby. And we got 4 x's here, so we'll have 3x on the outside, and x times x on the inside is x squared. That's the simplified version of that. Okay. You can use the blank to multiply binomial radical expressions. What are binomials? They are 2 names, 2 terms, a and b. So if you had ab times cd, what would you do? What would you do? What would you do? You would do what you've always done. Use some distributive action. Or as some people like to call it, foiling. I'm not a huge fan of the FOIL word. It works for what it is, but you can distribute, is what I'm going to say. Distribute. To multiply binomial radical expressions. So, let's do 1 together, and then I'll let you do b by yourself for some practice. We were going to distribute, here I would say, 4 times 5 And I would say 4 times 4 square root of 2. And then I would say 2 square root of 2 times 5. I'm going to put the 5 first because I like the way that looks better. And 2 square root of 2 times 4 square root of 2. That one, that's just going to be what that is. 4 square roots of 2. Okay, well, what's 4 times 5? 20. What's 4 times 4 times square root of 2 is 16 square root of 2. That's 10 square roots of 2. Okay. We can multiply the numbers on the outside. And then multiply these two under the same house. So that's 2 times 2. What's 2 times 2? 4. What's the square root of 4? 2. What's 2 times 8? 16. Great. Let me just bring all these things down. 20 plus 16 square root of 2 plus 10 square root of 2 plus 16. Looks like we have some things we can put together. Like the square root of 2's and the 20 and the 16. So let's do these guys first. 20 and 16 is 36 plus 16 square root of 2 plus 10 square root of 2 is 26 square roots of 2. Great. So good. Okay. You're going to do the next one. Because you can. You got these big giant brains. You should get to use them sometimes, you know? Like you should get to do some of that practice. That mental weightlifting that you need in order to grow your mind. Grow your mind. Yeah. Oh, yeah. Oh, yeah. All right, we talked about multiplying. So obviously we got to talk about dividing. Dividing. You can divide radicals if and only if they have the same index. They have the same index. All right. So in this example, we have the cube root of 48 divided by the cube root of 2. Do they have the same index? Yes. That's 3. So that really is the cube root of 48 divided by 2. Well, what the devil is that? 48 divided by 2, that's 24. So this is really the cube root of 24. I wonder if we could break that down. Let's give it a try. 24 breaks down into 12 and 2, and 12 breaks down into 3 and 4, and 4 breaks down into 2 and 2, and... Oh, by golly! My index is 3. I'm looking for 3 things that are of a kind. 3 of a kind. I got 3 of 3 twos, and there we go. So it's really 2 times the cubed root of 3. Look at you pretty little thing, you. That's so nice. So nice. Alright, this next example, they're already being divided by each other. Like they already combined it. But I don't know what 27 divided by 8 is. Seems like a weird number. So I'm going to go back the other way. I'm going to make this the cubed root of 27 over the cubed root of 8. Because I know the cube root of 27, and I know the cube root of 8. Alright? 27 breaks down into 9 and 3 and 3 and 3. We're looking for groups of 3, which we got. So that is 3. And I know the cube root of 8. I know everything about the number 8. It's my favorite number. Cube root of 8 is 2. Delicious. So this is really 3 halves. Yeah. Oh yeah. Alright, and then this example, my loves. Oh, we can do the division because they're both square roots. Huh. But 3 divided by 8 is not going to be super helpful. I wonder if I can break square root of 18 down. Let's see what happens there. 9 and 2 and 3 and 3. Okay, so the square root of 18 is really 3 square roots of 2 over the square root of 3. Huh. You know what the problem is? We're not allowed to have square roots in the denominator. Can't have roots in the denominator. Can't do it. Not allowed. Why? It goes back to ancient times when we did division longhand. We didn't have calculators to do our division for us. As you may know, the square root of 2 is 1.414 and some change. And dividing by decimals like that is not great. Right? Dividing by an irrational number is pretty awful. So what they decided to do was rationalize the denominator, make it from irrational to rational. And the way you do that, if you have a single term like this, is just multiply by that denominator. What are we going to get on the top? Square root of 3 times square root of 2. We know that we can multiply the numbers on the inside together. So this is the square root of 6 over 3 square root of 2 times 2, which is 4. We know the square root of 4 is 2. So this is really square root of 6 over 3 times 2, which is the square root of 6 over 6. Now, if we did division by hand, we would just be dividing by 6. That's a lot easier than dividing by 3 times 1.414 bloop, 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 bloop. That's our answer. Great. So good. We got one more page of notes. We're going to get it. You ready? I'm ready. I am so ready. Sometimes the denominator is a sum or difference involving radicals. A sum or a difference involving radicals. If the radical expressions are square roots, you can rationalize the denominator by multiplying the numerator and the denominator by the conjugate of the denominator. So if the radical expressions are square roots, you can rationalize the expression by multiplying the numerator and the denominator by the conjugate. Conjugate. Okay, so the conjugate, if I have something that is the square root of a plus the square root of b, the conjugate would be the square root of a minus the square root of b. Conjugate. Similarly, if I add the square root of a minus the square root of b, the conjugate would be the square root of a plus the square root of b. When we multiply by that conjugate, magic happens and we no longer have a squirt in the denominator. So let's check, shall we? I think we shall. Rewrite the expression with a rationalized denominator, meaning it no longer has square roots in the denominator. I see that we have subtraction between two square roots. I know that I can multiply by the conjugate, which is the square root of 5 plus square root of 2 on the top and on the bottom. Alright, let's do some numerator action over here. Numerator. And then we'll work on the denominator. And then we'll put them together. The numerator says 3 square root of 2 times square root of 5 plus square root of 2. Let's do some distributing. 3 square root of 2 times square root of 5. I can multiply the numbers underneath the square root because they are both square roots. The index is the same. So this is the 3 square root of 10 plus 3 square root of 2 times square root of 2. That's 3 square roots of 4. But hold on, square root of 4 is 2. So that's 3 times 2, which is 6. So my numerator is 3 square root of 10 plus 6. Denominator, we got to do some distributing. And then magic will happen. We will no longer have a square root in this at all. No square root in the denominator. Square root of 5 times square root of 5 is 5 times 5 is 25. Square root of 25. Well, hold on, that's just 5. Cool. Square root of 5 times square root of 2 is square root of 10. Negative square root of 2 times square root of 5 is negative square root of 10. Negative square root of 2 times square root of 2, that's minus 2 times 2. Inside there is 4. Oh, hold on, that's just 2. And hold on, this plus and minus cancel each other out. So I really just have 5 minus 2, which is 3. So we have, as our answer, 3 square root of 10 plus 6 all over 3. You know what? I see something here. I see something. I could take out a 3 from both of these. It would be 3 times the square root of 10 plus 2 divided by 3. Square root of 10, I don't know why I made that so large, plus 2, 2's on the outside. That's our final answer, the square root of 10 plus 2. Okay, so good. This last example looks delicious and juicy. Rationalize the denominator and simplify. Well, we're going to need to multiply by the conjugate. I see a minus here. That means the conjugate's got a plus. 4n plus 2 square roots of 2n squared. 4n plus 2 square roots of 2n squared. You know what else I see? We could have taken a 2 out of everybody first. Yeah, let's do that. I'm not doing all that work. I'm going to do less work. I'm going to take a 2 out of here. That's 2 times 2. I'm going to take a 2 out of here. That'll be 2n minus the square root of 2n squared. Right, we took a 2 out of here, 2 out of here, 2 out of here. Those 2's cancel. So now I have negative 2 over 2n minus square root of 2n squared. So we can multiply this by the conjugate. 2n plus the square root of 2n squared. 2n plus the square root of 2n squared. And I'm going to let you finish this. I'm going to give you this delicious snack of a problem for you to finish off. Remember, you should have no square root in the bottom when you're done. Will you have an n in the bottom? You can have variables in the denominator. That's fine. Totally fine. You just can't have radicals in the denominator. You've got to rationalize, okay? Make them rational numbers, meaning numbers that can be written as fractions, and roots can't be written as fractions. So we're not trying to divide by them. Okay? I love you, scholars, so much to the bottom of my teeny tiny heart. I will see you next time. Keep on that hustle.